All right, hi everybody. My name is Ezra. I am a freshman at MIT. I'm one of the organizers for this year's HMMT education event. So we're super excited that you guys are joining us today for this class with Dr. Adam Hesterberg, who's going to be talking about Wagner's theorem. So I'd like to begin by just sharing a couple logistical ground rules. So this is a webinar. Feel free to use this Q&A feature. At the bottom, you guys can find it at the bottom of the webinar. There's a little Q&A with a little text box button. If you guys have questions, we prefer that you use this feature to ask them instead of asking them in the chat. And this also allows you to upvote your questions that you think are interesting. However, I'd like to remind you guys that when Dr. Hesterberg is talking, when he's taking his time, he is taking his time out of his day to share this lecture with us. And we're super grateful for this, but we want to remind you guys just to be respectful to the classroom and to your peers. And if we don't think you're following this, then we'll remove you. But that doesn't have to happen. And this is going to be an awesome class. So with that, I would like to introduce Dr. Adam Hesterberg. And now I'm going to give you the spotlight. Just a second. Oh, I think, are you already spotlighted? Add spotlight. Okay. All right, awesome.
Hi, everyone. So the blurb for this talk seems to have been missing from the catalog. I'm glad that many of you are here anyway. Well, everyone hearing this is here, presumably. So we're talking about planar graphs. As a warm-up, while a few people are still trickling in, there are 6 graphs drawn at the right here. How many of those 6 graphs are planar? Raise your hand in the Zoom raise hand feature if you think that exactly 0 of these 6 graphs are planar. Okay, raise your hand if you think that exactly 1 of them is planar. Okay, a few hands, lowering hands. Now raise your hand if you think that exactly 2 of these 6 graphs are planar. A few more hands. Okay, and raise your hand if you think that at least 3 of these 6 graphs are planar. Also quite a few hands. Okay, so the correct answer is 2. We will be proving that over the course of today. So here, this graph G1 is a planar graph. We have in fact drawn it in the plane with no edges crossing. That's what it means for a graph to be planar. This graph G3 below it is also a planar graph. So being planar, for a graph to be planar means that it can be drawn in the plane with no edges crossing. This graph is not drawn with no edges crossing. There's a crossing here. So this is a non-planar drawing. But the graph is planar because there exists a way of drawing this graph so that no edges are crossing. In fact, this is the same graph as G1. So it can be drawn with no edges crossing. It's also planar. And these 4 graphs are all not planar, but we'll need to prove that. So I've given non-planar drawings of them. In each of these drawings, there is a place where 2 edges cross. But that doesn't mean that the graph isn't planar. Maybe there was some clever way to draw these so that no edges crossed. I could certainly have gotten closer to having no edges cross. For instance, if I had drawn this edge between this top left vertex of G4 and this bottom right vertex of G4, like this instead, that would be fewer crossings, although I still haven't gotten to a non-planar drawing. There are still some crossings left. So if we're going to prove this non-planar, we'll need some way of proving it for all possible drawings at once. Okay, background check. Raise your hand in the Zoom chat if you have heard of Euler's theorem. Statement is given here about the number of vertices, edges, faces, and maybe connected components of a planar graph. Okay, and now raise your hand if you are participating in Zoom hand raising things at all. So I can get the denominator. Okay, so most but not all of the people participating in hand raising have heard of this theorem. So I will prove it quickly. First, the statement is an equality between the number of vertices of a graph, the number of edges of the graph, the number of connected components of the graph, number of components where you can get between any vertex in the component by following edges, like this graph G6 has one component there and one component there. Those are connected components. And the number of faces in a planar drawing of the graph. Note that before we have this theorem, we don't know whether a planar graph has drawings with different numbers of faces. Like a priori, you might think that a graph can be drawn in the plane one way with some number of faces, some number of regions that the edges divide the plane into, or some different way with a different number of faces. But once we've proven this, since this, the number of vertices, and this, the number of edges, and this, the number of connected components of the graph, all only depend on the graph and not how we draw it in the plane. The number of faces of any planar drawing also only depends on the graph. In case any of this notation isn't clear, these are the number of vertices, the number of edges, the number of faces. Faces are regions separated by edges. And this is the number of connected components. So for instance, in this graph G1, which is planar, and here's a planar drawing of it, the number of vertices is 4, the number of edges is 3, the number of faces is just 1. There's just one infinite region, no edges separating things, and the number of connected components of the graph is 1. And this equality holds. 4 minus 3 plus 1 is indeed equal to 1 plus 1. So proof of this will induct on the number of edges of a graph. That is, we'll prove by induction on K that the above is true for all graphs G with K edges. So we need a base case. If a graph has no edges, there's a question, would we call the region in G3 a face? So this theorem applies if we have any planar drawing of a graph. G3 is not a planar drawing. Faces are something we only define for planar drawings. So we don't even define whether this thing is a face or not. So if the number of edges of a graph is 0, then there aren't many possibilities for what the graph is. So your graph has just a few vertices. Maybe that's your graph. If there are no edges, then your planar drawing also isn't anything interesting. You just put the vertices somewhere. So if the number of edges is 0, the number of faces of any planar drawing is definitely 1. You can definitely get from anywhere in the plane to anywhere else in the plane without passing through an edge because there aren't any edges to pass through. And the number of connected components of the graph equals the number of vertices, because every vertex is its own connected component. You definitely can't get from any vertex to any other vertex by following edges because there aren't any edges to follow. Number of connected components is equal, and therefore this statement is true. Number of vertices minus 0 plus 1 is indeed equal to 1 plus the number of vertices. Suppose we know the statement for k, and we want to prove it for k plus 1. Now, if we want to prove this statement for k plus 1, we want to prove something for all graphs G with k plus 1 edges. We'll need to start with an arbitrary graph with k plus 1 edges. If we were proving some statement without this for all quantifier, you might start with a graph on k vertices and add something to get to a graph on k plus 1 vertices. But I want to make sure that we actually get to every graph with k plus 1, sorry, edges, not vertices, this way. So let me take an arbitrary graph, G, with k plus 1 edges. And let me delete any edge to get a graph G prime. Call the edge we've deleted E, so G prime is G minus E. This is notation for G delete the edge E. By induction, we know something about this graph G delete E. It is a graph with at most k edges, so we know Euler's theorem is true for it by induction. And now we want to put the edge back and see that Euler's theorem is still true for this. So what we know is this statement for G prime. Now, when we put an edge back into the graph and the planar drawing of it, there are two things that could happen. Maybe we connect two connected components. So here is some graph, and here's an edge E that we had deleted before and now we're putting back. Maybe it connects two components that weren't connected before. So that won't change the number of vertices of the graph. We're adding 1 to the number of edges. We're not changing this constant 1. If we've connected, if these two vertices were part of different connected components, and now we've connected them by an edge, we've reduced the number of connected components by 1. We haven't changed the number of faces, because the only way we could have changed the number of faces is if we separated these two areas of the plane from each other by this edge. But if we just go around one of these connected components, we can still get there even after we add this edge in. So when we restore an edge between two distinct connected components of G prime, then we change the number of vertices by 0, the number of edges by 1, the number of faces by 0, and the number of connected components by -1. Note that we're subtracting number of edges of the graph, so this equality is still true. The other thing that could happen is that we could restore an edge that is not between two connected components. So this one was between two distinct connected components. If we restore the edge not between two connected components, again, I can draw what's happening. So we have some graph, some vertices, maybe it has multiple connected components, and we're restoring, say, this edge between vertices in the same connected component. Then we're not changing the number of connected components. These two vertices were already in the same connected component. They still are. We can still get between them by following edges, even without this one. But now we have increased the number of faces by 1, because if you could get from here to here by some path, then whatever vertices are inside the path would have to be a connected component. If there are edges crossing this path, you can use them to get from this vertex to elsewhere. So in this case, the number of vertices again changes by 0, the number of edges changes by 1, the number of faces changes by 1, and the number of connected components changes by 0. So again, this is still true by induction. Okay, if that was review, then well, we're moving on now. And if not, this may have been too fast. You can think about this as we move on. So I started by saying that I wanted to figure out how many of these graphs are planar. Let's now prove that this graph, G2, is not planar. So here's a non-planar drawing of it. Maybe there is some way of drawing it that is planar. How do we prove that that isn't the case? So there is no, way of drawing this graph planarly. Well, we can use Euler's theorem. So moving over here. We just proved Euler's theorem. Let's apply that to this graph G2. Suppose, for contradiction, that this graph G2, which incidentally is also called K5, the complete graph on 5 vertices, K is the first letter of complete in German, I guess, has a planar drawing. Then let's plug this into Euler's theorem. So we can count some of these things. So the number of vertices of this graph, G2, is 5. no matter how we draw it. That's just a property of the graph, 5 vertices. And the number of edges of G2 is 10, no matter how we draw it. Also, the number of connected components is 1, also just a property of the graph. So the number of faces in our planar drawing would be, let's see, 2 plus 10 minus 5 is 7. Also, each face of G2 has 3 edges on its boundary. Let's say at least 3. If we had a face with only 2 edges on its boundary, then we would have 2 edges connecting the same pair of vertices, but that doesn't exist in this graph G2. So each face of G2 has at least 3 edges on its boundary. And each edge is on the boundary of at most 2 faces. Edge has 2 sides. Those might be the same face or might be different faces, but anyway, at most 2 faces. So the number of face edge bounding that face pairs is, well, on the one hand, there are 7 faces apparently. And each of those faces has at least 3 edges on its boundary. So the number of face edge pairs is at least 21. On the other hand, each edge is on the boundary of at most 2 faces. There are 10 edges, and each of them is on the boundary of at most 2 faces. So the number of such pairs is at most 10 times 2 is 20. And that's a contradiction. So this graph must not have had a planar drawing. If you want to try proving something like this for yourself, see if you can figure out how to adapt this proof to prove that this graph G4, which incidentally also has another name, this is called K sub 3, 3, a complete graph on 3 and 3 vertices, is also not planar. Almost the same proof will work. You'll need to figure out some adaptation though, because if you do exactly this calculation with some number of faces, 3 edges per face, and 2 faces per edge, you don't get a contradiction. But let's move on. So we have that 2 of these graphs are planar, 2 of them are non-planar. Now I want to try to prove that either of these graphs is non-planar. Can anyone explain why this graph G5 is not planar? By asking a question in the question and answer panel, saying how you can prove that this isn't planar. Yeah, lots of people say that it contains or is basically this or something. So we need to be a little careful about what we mean by contains. Specifically, we want to say that if we could draw this graph in the plane, then we could also draw G2 in the plane. And we know we can't do that, so we must not be able to draw this in the plane. So if we had some way of drawing this in the plane, then, well, we could take our planar drawing, draw an edge between this vertex and that vertex that just follows whatever path these 2 edges followed, ignoring this vertex. And just don't even bother drawing this edge or that vertex. And then you would have a drawing of G2. So reroute an edge through this vertex of degree 2, and delete this, and you get a planar drawing of G2, which doesn't exist. Great, good answers, everyone. So this was not really a new example of a non-planar graph. It was just using this G2 thing again. Note that these were sort of different in a way that this one isn't. Like, there isn't a copy of G2 in this. There isn't a copy of K5 in this graph. For instance, all of the vertices of K5 have degree 4, but here the vertices have degree 3. And there isn't a copy of K33 in this graph K5, G2. For instance, this graph has 6 vertices and that one has only 5. So I did give you 2 different non-planar graphs here, and this one was sort of a silly example because it just contains G2. Okay, G6 is a little trickier to prove non-planar. Can anyone say in question and answer chat how to prove that G6 is not planar? Okay, so it contains K5 in some sense that we will make precise in a moment. Let me first draw on this graph something. So let's look at these 5 sets of vertices. One set of vertices, that single vertex, this set of vertices, this set of vertices, and this set of vertices. Not including those in any of the sets. The connections between these sets of vertices are in the same structure as this graph G2. Each of these 5 sets of vertices has some at least one edge to each of these other sets of vertices. And these are connected. So if we could draw this in the plane, then we could draw K5 in the plane, which we know is impossible, by rerouting edges. So like, let's suppose that we could draw G5 in the plane somehow. Draw this graph G6 in the plane somehow. And these 5 vertices are somewhere. There we go. So who knows where I've drawn them? And now, suppose I want to draw G2 in the plane. Well, I can just pick one of these vertices, say this one, to be this bottom vertex of G2. And whenever I want an edge through here, I can draw the edge along this one. Whenever I want an edge through here, I can draw an edge along this one. If I could draw this in the plane, then I could also draw G2 in the plane. Let me draw that in full generality because this example is getting a little muddled. So definition, if G is a graph and E is an edge of it, then G contract E, written as G slash the other way, E, is the graph formed by making the endpoints of E a single vertex. So here's a graph. And an edge E. And if I contract that edge, I make its endpoints a single big vertex. So there's a nice big vertex. And put edges where you'd expect between this new vertex and any vertex that was adjacent to either endpoint of E. If I could draw this graph in the plane, then I could also draw this graph in the plane by just drawing this vertex smeared out over a big area. Or if a vertex is supposed to be a point, which it is in our definition of planar drawings, then instead of smearing out a vertex, I could put the vertex at just one endpoint, but draw all of the edges very close along this old edge that I contracted. So if I can draw this graph in the plane, then you can draw the contracted version in the plane this same way. So back over here, if I could draw this in the plane, well, if I contract this edge and 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 this edge, contract all of those edges within each of these purple components, then you get G2. So if I could draw this in the plane, then after each of those contractions, I could draw it in the plane by rerouting edges this way. And then I would get a drawing of G2. Okay, so we can't draw that one in the plane. And again, I sort of didn't give you a new example. This graph G6 was not planar just because it contained this graph G2. So am I a bad person for not giving you new examples, for making you stick with just these two? No. So the thing we're going to prove is that these are the only two basic examples, that every non-planar graph is non-planar because it contains one of these in roughly this sense. So let me define that. Graph G contains the graph H as a minor, if and only if you can get from G to H by some combination of deleting vertices, deleting edges, and contracting edges. Note that deleting vertices and deleting edges also preserves planarity. If you have a planar drawing of a graph and then you delete some vertices, you have a planar drawing of a new graph. And the theorem that we just proved by pictures over here is that if G is planar and H is a minor of G, which I will write as G greater than or equal to H, then H is also planar. Or conversely, if H is not planar and G contains it as a minor, then G is not planar. So any graph that contains K5 or K33 as a minor is not planar. So G contains K5 as a minor, or G contains K33 as a minor, G is not planar. Then the theorem that we're going to prove in the remaining 10 minutes of class, and we won't actually finish a proof. I will cheat twice during the proof. You should call me out if you think you see one of the places I've cheated and then try to fix it yourself. So theorem by Wagner in 1937 is that every graph G, either, let's say for every graph G, either G is planar or G contains K5 as a minor, or G contains K33 as a minor. So this theorem is that you can't have none of these. This theorem is that you can't have both a planar graph and one of these conditions. And Wagner's theorem says that you can't have none of these. Incidentally, this is also very closely related to theorem of Kuratowski from 1930, which is that for every graph G, either G is planar or G contains a subdivision of K5 as a subgraph. Subdivision is where you can take an edge and divide it up into multiple edges by putting vertices on it. Or the same thing for K33. This is a stronger theorem and was proven earlier. So really Kuratowski deserves most of the credit, but Wagner's proof is nicer and this way of thinking about things by minors is nicer. So they're slightly different theorems, and we're going to do basically Wagner's proof. So proof of Wagner's theorem. Well, we started out today by inducting on the number of edges in a graph. We're going to do that again. So we'll induct on the number of edges in this statement of Wagner's theorem. Base case, if G has no edges, then G is planar. So it is indeed the case that one of these three conditions held. For the inductive step, excuse me, we have a graph with at least one edge. So suppose that the number of edges of a graph G is k plus 1, which is at least 1. Let's pick one edge. And contract it. So we get a graph G contract E. If G contract E has a K5 minor, then G also has a K5 minor. And we're done. Similarly, if even after we contract, this graph has a K33 minor, then great, we're done. So this third condition is what we care about. What if after we contract E, we get a planar graph? So let me draw G contract E. So here is some vertex E that was made by contraction. And we have some planar drawing of a graph around it. So here's a graph. And in this drawing, E, this new vertex, is in some face of the graph that we would get if we deleted E. So here is the face that we care about. So in G, contract E, and then delete E, delete the new contracted vertex. In that planar drawing, E is in some face. And let's let the cycle that bounds that face be C. So this is the cycle C. And now we're going to try to put back in this vertex E, or E is adjacent to some of these vertices. We're going to try to uncontract E and either get a planar drawing of the original graph G after we uncontract E, or find a K5 or K33 minor. So let me redraw this cycle. And let's say that this edge E had endpoints U and V. U and V. So let me take any vertex adjacent to U somewhere on this cycle. In fact, let me take a vertex that's adjacent to, well, if there is no vertex adjacent to U, then I can draw this graph in the plane just by drawing V, connecting it to all of its neighbors, like this vertex E was, and then putting U up very close to V. So if U has no neighbors, do this to draw the original graph in the plane. If U has a neighbor that is not a neighbor of V, then go around the cycle until you get to a neighbor of V in each direction. So here's a neighbor of V, here's a neighbor of V, no neighbors of V in here. Now, if there are no neighbors of U in this part of the arc, then we've successfully drawn this in the plane. If there are neighbors of V in this arc, of U in this arc, pick one of them. So the graph has this stuff in it. And then I've found a K33 minor. So these 6 vertices and the edges between them are exactly a K33, that graph from before, where each of these 3 vertices is adjacent to each of those 3 vertices. So we found a K33 minor. And finally, last case. So I started by picking a vertex that was adjacent to U but not V. What if those don't exist? What if every vertex that's adjacent to either U or V is adjacent to both of them? Well, if there are only 2 such vertices, we can draw our graph in the plane again, like this. But if there are 3 vertices adjacent to both of them, so we can't draw it in the plane, then these 5 vertices are a K5 minor. Okay, and doesn't look like anyone has caught me cheating. The place I cheated was in saying that the boundary of this face was a cycle. Maybe there's some extra stuff sticking out from the boundary of this face, and I will leave it to you to think about how to deal with that. We have about 30 seconds left for questions. Summary of the proof. I picked any edge, contracted it, got a planar graph, uncontracted, looked at trying to draw in the uncontracted edge, and either succeeded at drawing it in, and so got a planar graph, or found a K5 minor, or found a K5 minor, or found a K33 minor.
All right, awesome. Thank you, Dr. Hesterberg. That was an awesome talk. And I want to thank all you guys for attending. So it's 2:35 now about. The next session, session 3, will start at about 2:40. So if you guys want to hop off the Zoom and join your next class, then you're welcome to do that. Otherwise, just have a nice day.
The whiteboard on which I drew for this class has a link in chat now. Thanks for coming. Bye.